All right, let's unlock some secrets today. You've given us these Korean lecture notes on the natural log function, ln of x.
ln of x.
I'll admit my initial thought was, oh boy, back to high school math.
Right.
But there's something, I don't know, there's something so intriguing about a function that even I remember after all these years.
Yeah. And you're right to be intrigued. The natural log function ln x, it doesn't exist in isolation. It is deeply intertwined with the exponential function e to the x.
Yeah.
And they're like a power couple in that way. Like understanding their connection kind of unlocks a whole nother level of insight, I think.
Okay. I'm liking this power couple idea already. But before we dive into their relationship drama, can we just give people a quick refresher on what makes each of them unique? I feel like we need their individual bios before we delve into their combined story.
Absolutely, yeah. So imagine the exponential function e to the x as representing unstoppable growth. Right. So whether it's a colony of bacteria that's like doubling in size every hour, or it's compound interest in your bank account, that's quietly multiplying in the background. E to the x captures that idea of like the bigger it gets, the faster it grows.
Okay, that makes sense. Exponential growth, it definitely has that snowball effect.
Totally.
But where does the natural log fit into all of this? It seems much less, I don't know, dramatic at first glance.
Sure. So that's where things get interesting, right? So the natural log, ln x, is like the decoder ring for e to the x.
Okay.
It gives us a way to answer questions like, how long will it take for my investment to double? Or what is the growth rate of this bacteria population?
Yeah.
And it essentially translates the language of exponential growth into something more manageable.
So instead of just seeing something growing really rapidly, lnx helps us analyze the how and the how fast.
Exactly. And this power couple analogy goes even deeper, right? So if you were to graph ln x and e to the x, what you would find is that they're perfect mirror images of each other reflected across a diagonal line. And what this reflects is their inverse relationship. So they essentially undo each other mathematically.
Wait, so if I plug a number into lnx, get the result, and then plug that into e to the x, I'll end up right back where I started.
Exactly.
That's wild.
It is. And this, what seems like a simple relationship, it has massive implications that we'll get into a bit later. But for now, just keep in mind that this mirror image property on the graph isn't just a visual quirk. It points to this deeper connection that we'll unpack further.
You've definitely piqued my curiosity. Now, the notes mention lnx being a strongly increasing function.
Yeah.
What exactly does that mean, and how does it relate to this whole exponential growth idea?
Good question. So strongly increasing simply means that as x increases, lnx also increases, and it never slows down, it never plateaus. And this relentless upward climb is directly related to its connection with exponential growth. Remember how e to the x represents this ever-accelerating growth? Well, ln x is capturing that same acceleration just from a different perspective.
So it's not just that lnx is increasing, it's that it's always gaining momentum as it goes.
Precisely.
Yeah.
Now, if we picture the graph of ln x in our minds, this upward momentum is reflected in its shape. It has this elegant curve to it that always bends upwards, and we call this being concave up.
Okay, I'm starting to see how all of this ties together visually.
Yeah.
But the notes also mention something about lnx having a surprising effect on multiplication.
Yes.
Something about turning it into addition.
You're right. And this is where the true power of the natural log starts to shine through. So imagine having to multiply two really large numbers together.
Right.
It can be a tedious process. But the natural log has this incredible ability to transform multiplication into addition.
Hold on, you're saying lnx can make complex multiplication as simple as adding numbers together. That sounds almost too good to be true.
It's not magic, but it's close.
Yeah.
Mathematically, it means that ln(ax) is exactly the same as ln(a) plus lnx.
Wow.
And this property has really revolutionized fields like engineering, physics, even finance.
Okay, I need a real-world example here. How does turning multiplication into addition actually play out in, say, finance?
Sure. So imagine trying to project the growth of an investment over time.
Right.
Dealing with compound interest can quickly lead to some messy calculations. But by using the natural log, what financial analysts can do is essentially transform those complex multiplication chains into much simpler additions. It's like a shortcut through the computational jungle.
So lnx is like the ultimate financial planner's tool then, helping them navigate the the complexities of compound interest without getting lost in a sea of numbers.
Exactly. And this ability to simplify calculations is just one of its superpowers. Remember how we talked about reciprocals earlier?
Right.
The natural log have a special relationship with those as well.
Right. There was something in the notes about how ln x kind of elegantly handles those 1x situations.
Yeah, so it boils down to this. Taking the natural log of a number
Mhm.
and its reciprocal gives you the same value, but with opposite signs.
Okay.
So ln2 would be the negative of ln12.
It's like this perfect symmetry embedded within the function itself. Okay, this deep dive has been full of aha moments already.
Yeah.
But I have to admit, the notes kind of lost me a bit when they started talking about the range of ln x and using integrals to define it.
Sure. So these are concepts that sound very intimidating, I think, to a lot of people. But they're really just different ways of understanding the depths of ln x. So let's start with the range. So the lecture notes use some pretty fancy mathematical notation to say that the range of ln x includes all real numbers.
Okay, back up a second. Range, is that like the territory that ln x covers on a graph?
You got it. It means no matter how high or low you go on the y-axis, you could always find an x value that ln x will hit. Its potential output is limitless.
Okay.
Think of it like this. Imagine stretching the graph of ln x infinitely far in both directions.
Okay.
No matter how far you stretch it, it'll always keep going, covering every single point on the y-axis.
Wow, so even though it's grounded on one side, it can never go past 0 on the x-axis?
Right.
But its reach on the y-axis is unlimited.
Exactly. Now, as for the integral definition, this is where things get really elegant. So instead of just describing what ln x does, we can actually define it using the concept of area.
Area, like the area of a square or a triangle. I thought we were talking about functions and logarithms.
Right. So imagine the graph of 1x.
Yeah.
The integral of 1x from 1 to any number, let's say 2, represents the area under that curve.
Okay.
And guess what? That area is precisely equal to ln2.
Wait, so the natural log of a number can be represented by an area under a curve. That's a mind-bending connection.
It is.
Yeah.
And the size of that area changes as x changes. And it beautifully reflects the properties of ln x that we've already discussed. For example, remember how ln x is always increasing?
Yeah.
Well, the area under the curve of 1x also keeps growing as we move to the right on the x-axis, mirroring that behavior.
Okay, that visual connection helps a lot. I'm starting to see how the integral definition isn't just, I don't know, some abstract formula,
Right.
but a way to connect ln x to this very concrete concept of area.
Exactly. And this is where the beauty of mathematics, I think, really shines through, right? We can express the same concept, the natural log, in these different ways, each revealing kind of unique aspects of its nature.
It's like having multiple lenses through which to view this fascinating mathematical object. But before I get too lost in the elegance of it all, the notes mention something called the fundamental theorem of calculus in this context, and it sounded pretty important, but I'll admit I'm a little fuzzy on the details.
The fundamental theorem of calculus. This is like the grand unifying theory of calculus.
Yeah.
It connects two seemingly disparate concepts, derivatives and integrals.
Okay, remind me again. Derivatives are about like slopes and rates of change.
Yes.
And integrals are about areas.
You got it. And what seems so incredible is that these two ideas, which seem to be on completely different sides of the mathematical universe, are fundamentally linked.
Sure.
That's the beauty of the fundamental theorem of calculus. It tells us that differentiation and integration are essentially inverse operations.
Yeah.
They undo each other.
So it's like that power couple analogy again.
Exactly.
But instead of ln x and e to the x, it's derivatives and integrals working together behind the scenes of calculus.
Exactly. And when we look at the natural log through the lens of the fundamental theorem, we discover yet another layer of elegance here. Remember how we defined ln x using the integral of 1x?
Yes, the whole area under the curve idea.
Right. Well, if you differentiate ln x, meaning you find its rate of change, what you get is 1x. It's this beautiful full circle moment where the derivative of ln x takes us right back to the function we used to define it in the first place.
Wow. So the natural log, its derivative, and its integral are all interconnected in this elegant dance. It's like we've uncovered this hidden network of mathematical relationships.
And that's just it. Right? Math isn't just about memorizing formulas. It's about understanding these deep, often surprising connections. But, for all the insights I think we've gained today, there's always more to discover. For instance, we've talked about the properties and the definition of ln x, but how would you actually calculate it for a specific number, say ln2?
That's a really good question. I have no idea where to even start. It feels like we've been exploring the map of LNX this whole time, but now you're asking me to actually navigate the terrain.
And that, my friend, leads us to the world of numerical methods and series approximations, which are incredibly powerful tools for estimating values like ln2 with remarkable accuracy.
It's amazing how much complexity lies beneath the surface of something that we often take for granted. I have to admit, I started this deep dive thinking I'd be relearning some dusty old math concepts, but it's really turned into a journey of discovery.
And that's the beauty of it, isn't it? The natural log is just one example of how a seemingly simple concept can open a door to a universe of interconnected ideas, really revealing the elegance and the power of mathematics.
It makes you realize that there's always more to learn and explore. Well, on that note, I think we've successfully navigated the fascinating terrain of the natural logarithm today.
Indeed we have. Until next time, keep those curiosity engines running. And remember, there's always another deep dive waiting just around the corner.
I can't wait.